In this lecture, I am going to explain you what is called the cubic closed pack structure and hexagonal closed pack structure. Let's first see what is cubic closed pack structure, how it is formed. As you know that atoms arrange themselves as close as possible to reduce the potential energy. In this case, all atoms are of the same size. If they are of the same size, then they will be packed the way it is shown in this diagram. And let us say it form a layer A. It is just like, if you arrange the tennis balls on the surface, they will arrange themselves like this. Then we are going to put second layer of atoms on the first layer such that the atoms in the second layer will sit in the depression formed by layer A. As they are spherical, atoms are spherical, and so they will occupy these depression positions. So let's add second layer, layer B, and as you can see that they are arranging themselves in this fashion, and these atoms are sitting in the depression formed by atoms in layer A. Then we are going to add third layer, that is layer C. Now layer C we are going to add such that they will sit in the depression. I have shown some hollow atoms so that you can see the depression. So the third layer atoms will occupy the depression position formed by layer B. So they will sit in the depression, but they will not be exactly above the atoms from layer A. Okay, layer C atoms occupy the depression position such that they will not be exactly above the atoms from layer A. So they will not sit here. If the atoms from layer C occupy this position, then that would be exactly above the atoms from layer A. So they will not occupy this position, but they can occupy this position or this position or this position. Let's see how they sit. So as you can see, okay, layer C atoms are sitting in the depression formed by layer B, but they are not above the atoms in layer A. If this is the case, they form a stacking like ABC, ABC. This kind of stacking is called ABC, 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 and so on. When such a stacking takes place, it forms a FCC structure, which is called CCP, cubic closed packed structure. Cubic closed packed structure is FCC structure. Then let's see how HCP is formed. Next one is hexagonal closed pack structure. In hexagonal closed pack structure, layer A is as it is. Then layer B atom sits in the depression formed by layer B. Same. But now layer C sits in the depression formed by atoms in layer B, and they are exactly above the atoms from layer A. So they can occupy this position. So they would be exactly above, or they can occupy this position. So that layer C atoms would be exactly above the atoms from layer A. Let's see. Okay, they are sitting exactly as I said. I have shown this one is hollow and it sits exactly in the depression formed by layer B, and they are exactly above the atom from layer A. This kind of stacking is called AB-AB, and this hexagon AB-AB stacking gives us hexagonal symmetry. So this is called the HCP structure, hexagonal close pack structure. Let us see the unit cell of HCP now. As you can see there, this is a bottom surface, that is layer A atoms. Then we are going to add layer B atoms, which sits in the depression formed by layer A. So this is layer B atoms. Then we will add layer C. Layer C atoms will sit in the depression formed by layer B, and they will be exactly above the atoms from layer A. So this is the third layer. So this is the unit cell of HCP. We will just turn this, we will get like this. Okay, that is the unit cell of HCP structure. Let us reduce the size of the atom so that you can see clearly. And see, we have just reduced the size of atoms, and you see the unit cell of HCP structure. Now here, what happens is HCP and CCP have the same density of packing and coordination number. Okay, they have same coordination number as well as same density of packing. Let us find in this case the coordination number. For that, consider this atom, or this you can see. Now you can see that in his own plane it is in contact with these six atoms. With these six atoms, they are in contact. So in the same plane, there are six nearest neighbors. Above plane, they are also, these are also in contact with this atom. So below the plane, there are three, and above the plane, there are three. So six in his own plane, three atoms in upper plane, and three atoms in lower plane. So the coordination number for hexagonal close pack structure is also 12, and you know that for FCC also the coordination number is 12. Now here density of packing is also same, that is 0.74, or packing efficiency is 74%. We are not calculating packing efficiency for this, that would be in the numerical. Physical and mechanical properties are also same for SCP and FCC. Then effective number of atoms are 6. Effective number of atoms are 6. Now you see, in this unit cell, in this plane there are 7, in this plane there are 7 atoms, and in the middle plane there are 3. Now there are 6 corners. This is 1, 2, 3, 4, 5, and 6. And also here 6. 1, 2, 3, 4, 5, and 6. So 6 here and 6 here. Contribution of, so total 12 are there. And contribution of each one to this unit cell is 1 by 6. So 12 into 1 by 6 is the contribution. Then consider this one and this one. These two are shared by 2 unit cells. So its contribution is half. So 2 into half plus these are the three. 1, 2, and 3. Three atoms. They are inside the unit cell. So its contribution is 3. And that's how effective number of atoms is 6. Coordination number I already explained to you, and that is about the SCP structure.